Yeah, today we will cover one topic that is not in our textbook. I think it actually is in the textbook in the sense that they continue that on somewhere else. So it is actually section 5.7. It's section 5.7, but they say you can find it on CD. But the thing is, I assume some of you don't have the textbook because you rely from my notes. Okay, so I will use my own examples later on, and I will post it later on. Okay, you practice from there, and you can also see this base theorem thingy from pretty much all of my test 3. Okay, so if you collect 10 of my test 3, 10 of my test 3, then you will find 10 different Bayes theorem problems. Okay, now Bayes theorem, this thing here is not in our curriculum, not in West LA College curriculum. In fact, I know it is not at East LA College curriculum, not in Santa Monica curriculum. But why I want to teach this, it seems like I'm insisting to teach this, to be more precise. Like people tell me you don't need to teach this, but I say I want to teach this. So I'm quite arrogant, huh? Okay, but the reason is because I teach this because of its usefulness. It's quite useful in our daily life. Okay, it explains a lot of phenomena that originally counterintuitive at first. Okay, now here's the thing though. Bayes' theorem itself is kind of okay. When I first learned Bayes' theorem, my professor actually gave us the formula right away. And once I look at the formula, and not only me, actually my whole class, when we look at that Bayes' theorem, the formula, we just skipped that section. We just like, nobody in my class was actually studying that, you know, and yeah, my professor figured out, and then she gave us quizzes basically every time we meet. Yeah, kind of like that. Basically, at first we didn't want it because the formula was so terrible. Okay, here's the given condition. Given probability of A is given, of course, consequently, probability of not A also given implicitly. And then probability of B given A is given. Probability of B given not A also provided. And then the question is, what is the probability of A given B? Well, Thomas, I don't understand it. Trust me. Me too. When I first saw it. Okay. I'm about to give you this a formula, and the formula tells us the following information: this thing, this thing, this thing. And because probability of A is given, implicitly probability of not A also given. Okay, now then the question is, what is the probability of A given B? The answer is probability of A given B is equal to probability of A times probability of B given A over probability of A times probability of B given A plus probability of not A times probability of B given not A. That's the formula. Now, again, when me and my classmates saw that formula, we just like forget it. I don't get it. And more or less, that's actually, of course, it's not a good thing that we ignore this lesson at that time, me and my classmates. But one good thing that we learned is that if you don't understand the formula, try to think about it. Okay, there's a reason why the formula looks like that. And yes, after a couple time, I think it's like around a couple of weeks or a couple of days to be more precise, we realized, yeah, my professor will always ask this question, and he or she, actually she, purposely make it such that this part becomes a big portion of our grade. So we realized that, we have to study this. Too bad. Okay, now, what I'm about to do right now is, instead of using formulas and these kind of notations, I prefer to use examples. Okay, I will teach this Bayes theorem using examples. And instead of attacking the formula right away, I will answer this question in 4 steps. Okay, now, so focus not on the formula. Okay, in fact, I don't think you need to memorize the formula. Later on, I will come back to this formula and explain why it looks like this. But let's see how to use that first. Okay, now suppose we have the following situation. I will explain it through examples. Actually, I would explain it using only one example. Okay, only one example, and then we replicate the idea through other examples also. I will use the following example here. Now, I need your input. What percent of our population are males? Just make up some number. What percent of our population are males? Okay, let me use 45%, okay? 45% of our population are males. Okay, now, so implicitly, what's the proportion for female? Then that will be 55% are females. You know what? I need to put this disclaimer this time quite explicitly. I need to put this disclaimer. This lecture may contain some sensitive topics. However, please focus on how we use Bayes theorem. All examples are hypothetical. Okay, so please, I have no intention whatsoever to offend anybody, and I will. So the thing is, like, Bayes theorem being used a lot in in many cases, and if you type Bayes theorem examples on YouTube, not YouTube, on if you Google it, then you will see that Bayes theorem being used in a lot of cases where it is actually quite sensitive for us. Okay, so yesterday when I tried to prepare this lecture and get some examples from internet, the first example I get was actually about cancer. You know, I told you that my family and I had cancer before in the past, right? Okay, but I'm fine talking about cancer, but for some people, it could be something we cannot get through yet. Like if my family currently still struggling with cancer with my dad, for example, then that if I talk about this right now, I may get a bit upset, maybe. Okay, that's why I want to give you this heads up that it could be quite sensitive, but please, we'll focus on how to use Bayes theorem. Okay, and all examples here are hypothetical. I try to not to use an example that is sensitive, but at the same time, you will see that Bayes theorem is used in making decision in sensitive cases. Okay, yeah. Now let's come back here. Somebody leave me a chat. Didn't we have this theorem step by step in one of our quizzes? I remember having to do this, huh? We did in our quiz. Yeah, no, not yet. As I know, not yet. I will give this as a part of your quiz later on. Yeah. Maybe you saw one of my old quiz. Yeah, and or my old tests that you see. Okay, now let's talk about one case then about left hand. Okay, like let's say 2% of males are left-handed, while 3% of females are left-handed. Okay, I don't think left hand is a big issue here, huh? Okay, I hope not. I hope not, please. By the way, I am a left hand actually. I'm actually a left hand. I write using right hand right now because you know I come from Indonesia, and in Indonesia, because of our culture, being a left hand is actually a taboo. So when I was in first grade, kindergarten and first grade, I remember my mom actually trained me to write using right hand. I originally used left hand, right? And then when my mom saw me, and then she will actually smack me, change my hand to right hand to write. And then when she left, I changed it back to left hand. Yeah, of course, my mom figured out from my handwriting that now your left hand writing and right hand writing still look different. That's how she actually figured out I actually use left hand. So she ended up actually tied my left hand to the chair, to the yeah, tie that to the to my chair such that when I write, I need to use my right hand. Yeah, so sad that one time they actually left me and I need to go to restroom. So I literally brought that chair together with me to restroom. Well, anyway, that's what happened. Yeah, here you call that child abuse. Back there they call that education. Okay, let's see this example. And the big question is, the big question that Bayes trying to answer, big question. What percent or what portion or what is the probability that left-handed is a male. That's the big question. Okay, now to answer this question, I will break it up into 4 steps. To answer this big question, I will break it up into 4 steps. Let me call that small questions. So instead of answer that one big question directly, we will do it in 4 steps by answering these 4 questions. The first one, construct the probability distribution, probability tree. And then second, find probability of randomly selecting male and left hand at the same time. Let me use LH. Find the probability of selecting female and left hand at the same time. And third one, then find the probability of selecting a left-hand person, regardless that's male or female. And then finally, find the probability of selecting a male, knowing that person is a left-hand. Okay, now the thing is, like, it seems like the informations we get here are so minimum. You know they're male or female. Once you know that person is male, then the probability left hand is 2%. Okay, now the question is, knowing that person is a left hand, what's the probability that person is a male? It's the other way around. Okay, so if I use notation, probability that it's a male is 45%, and probability of female is 55%. Oh, by the way, this is actually another place where it gets a bit sensitive to some people, that when I say male and female and somebody say, Thomas, what happened if with somebody who is not male and not calling themselves male or female, because gender is actually a spectrum. Okay, now I'm not going into that. I agree with that view, but the thing is, like, for the simplicity of our lesson, I will just make it into binary for now. Okay, male or female. Okay, now and then a good thing here, we talk about being left-handed. Okay, I don't think it's quite sensitive, but you can change this left-handed into the vote. Will they vote for Trump re-election, for example? Okay, or if 2% of males actually will vote for Trump, you should be happy. If 3% of females vote for Trump, then you should also be happy if you are a Democrat. Okay, so it can go both ways though. It applies to a lot of other things. Or you can also say that 2% of males actually going to STEM program. Okay, STEM program stands for science, technology, engineering, and math. Okay, so this is male, females, and then going to left hand, voting for Trump, going for stamps, or how about uh, like purple. By the way, I like purple, purple color. What else? 2% of males actually using iPhone, you know, because only 2% can afford iPhones, right? I don't use iPhone. I'm not that rich. I'm poor. And a lot of other things. Okay, so the starting points may be male and female, but there could be other thing also. One of the case that I use later on to analyze the election, and I will use the example of the election in Indonesia, is that somebody who say that they will vote for candidate A, and then if you don't vote for candidate A, they will be voting for candidate B, and the issue after that is, will they actually go to vote? You know, so I can say right now that I will vote for Trump, but I don't actually go to vote. Okay, I just say that I will vote for Trump, let's say for example, right? But if I don't actually go to vote, whatever I say right now doesn't count, you know. Okay? So it is your vote that count, not your opinion. Okay, yeah, but that this is where we are going to, and I will show you another case later on, the actual case of cancer that I had when I was diagnosed with one. Okay, let's start with this. So the first one, the probability 3. The probability 3. Okay, now earlier we saw that the first branching is male and female. The second branching is probability that left hand given that person is a male is 2%. Probability that that person is left hand given that person is a female. So once we know that person is a female, the probability that person is left-handed is 3%. By the way, I saw more female in America actually left-handed than males. That's actually the other way around compared to Indonesia. And this is my observation, so I cannot confirm that with actual numbers. But it's the other way around. In Indonesia, being left-handed is more common recently, but when I was in kindergarten, elementary school, it's a taboo. In fact, what do you feel if I tell you that that at one time, in Indonesia, when it's not like in America, they just give you the grades, but in Indonesia, they give you the grades and they actually rank you with your classmates. They put ranking. So rank number 1, the highest score in the total highest score is who, number 2 who, number 3 who, number 4 who. Okay. In my case, actually, I supposed to rank number 1, but I was dinked down to rank number 2 simply because I use left hand. So yes, at that time they have discrimination against left-handed people. So well, because of that, then I changed to right hand. So right now you can say I'm ambidextrous. That's by training, not by nature. Not by nature. Oh, by the way, you know that Mr. Obama is actually left-handed. As I know, Mr. Obama is left-handed. And there's one other president, I think that's Mr. Bush, also left-hand. According to history, we have higher proportion of American president left-handed. You know, but not Trump. As I know, Trump is not left-handed. Yeah, Mr. Obama and Mr. Bush actually left-handed. Yeah. Well, anyway, that's out of topic. I make left-handed a big issue because it was a big issue there in Indonesia. Here it's not a big issue. Okay, probability 3. Probability 3 will be done in the following way. The event is written at the end of the branch, male, female, and the probability for that event to happen from that in that branching is written on the branch. So for males is 45% and female is 55%. Now, every time you have a branching like this, then the total percentage or the probability has to be 100%. Every time you branch out, then the total has to be 100%. Okay? Or in decimal, the total has to be 1. Are you with me? Okay, so two things to say. The event is written at the end of the branch. The probability is written on the branch. Now, next. Knowing a person is male, the probability that person is left-handed is 2%. So, not left-handed, therefore, is not 43%, 98%. Remember I said that every time you branch, the total of the percentage or the probability has to be 100%. Okay. So likewise, for female, knowing that person is a female, the probability that that person is left-handed is 3% according to our passage above. Therefore, the probability that person not left-handed is 97%. Okay. Now, remember again, the event is written at the end of the branch, while the probability is written on that branch. It is actually okay for you to write this 55%, for example, or other probability below that branch. It's okay, it's acceptable. It's acceptable. It's just like the probability has to be on the branch, and then the event is at the end of the branch. Okay. I want to erase the coloring. So this is the probability tree. Now, part 2, step 2. Find the probability, if we select them at random, find the probability you have male and left hand at the same time. Male and left hand at the same time. Now, then the way we compute that will be male, probability of male, times the probability of left hand given its male. Okay, let me write it down. This is equals to probability of being male first times probability of being left hand given that person is a male. Okay, so you remember the conditional probability of left hand given male is equals to the probability of the intersection over probability of male, right? Imagine if you multiply both sides by this, if you multiply this to the left hand side, then the probability of intersection equals to the probability of male times this, male times this. Okay, so it is actually very much in line with what we learned before. Okay, very much in line with what we learned before. I just changed the way we write that formula. So male and left-handed. Now here it will be 45% times 2%. Now when you compute using percentage, especially if you multiply or divide, change them to decimal first. Okay, don't compute it directly. No, no, no. 45% times 2% is not 90%. No, it's not. Okay, so change it to decimal first. And then when you multiply, you will get 0.0090, which in percentage is 0.9%. Now this 0.9% is the proportion of male and left-handed at the same time in our population. Okay, if we don't know anything, we just select from the population, from whoever we can get. Okay, now then, being male is 45%. This is male, this is female. Maybe this is male and this is female. Okay, and a small portion of this is left hand. A small portion of this is also left hand. So left hand here, not left hand here. Try to imagine this situation. Now, if you select from this group as a whole, what is the probability you end up with this color here? This one here. What is the probability you end up with that? And the answer is 0.9%. So male and left hand at the same time is 0.9% of the whole population. Now this left hand here is 2% of the male. If you see that from male point of view, it's 2%. But if you see that from the whole male and female or whoever we get in our population, it's actually 0.9%. Okay, so try to imagine this structure here. I will erase it, otherwise it gets too complicated, too many things here. Now then, the second part, how about probability of female and left hand at the same time? Using the same view, then we see being female first and then left hand. Okay, so that will be probability of female times probability of being left hand, knowing that person is a female. That will be 55% times 3%. 0.55 times 0.03, we get 0.0165. So that's 1.65%. Then suppose now I select from the whole population. Suppose I select from the whole population. What is the probability of randomly selected person is left hand? Regardless that's male or female. Now then, for the left hand to happen, it's either this part here or this part. Okay. It's either male and left hand or female and left hand. Okay. Then this is equal to probability of male and left hand plus probability of female and left hand. Which both of them already computed in part 2. Did I use ABC or 1, 2, 3? 1, 2, 3. Okay, so we should this is 0.9% plus, or you can just make it decimal. Let me use decimal. 0.0090 plus 0.0165, which when I add, I get 0.0255. Okay, so this actually tells us that from our whole population, 2.55% actually left-handed. Okay. Now, if you want to make it quote unquote political, if you want to make this political for students' benefit, right? If you just want to file a lawsuit against a school with this percentage, then you can say that, you know what, it means that for every classroom for 40 students, and they need to prepare at least one of them a desk for left-hand person. Because, for example, I heard the case, now I cannot confirm this, okay? I heard it's UCLA, but it could be other university in which that when they have the lecture hall, all of the seats is actually designed for people with right hand, writing using right hand. And students who actually left hand have hard time actually to write on it. You know, like if it is right hand, then your hand can rest on the right hand side, but not on the left. So they actually file a lawsuit. Some students actually file a lawsuit against that university, requiring the university to prepare more seats for left-hand person. Okay, and then the university then need to do computation, what proportion of the population is left-hand. Therefore, they can prepare proportionally the number of desks accommodating left-hand students. Okay, I personally disagree with the way they make it. They make it like a lawsuit. It can be just a complaint. You know, I mean, the worst I would do. I'm speaking from a left-hand person also. Okay, I don't want to do lawsuit right away. You know, and try to do some adjustment. Okay, try to do it some adjustment. The way they make it feel like being left-hand is some kind of like a severe disability that we cannot fix ourselves. You know. Well, anyway, that's my view. That's my view. Okay, but so from here again, the number I use here is hypothetical. So it seems like we have 2% and 3% left-hand for male and female. But once we mix them together, okay, in a pool, then in total it's actually 2.55% having that having left hand. And you will see this phenomena that the minimum percentage is 2% and the other one is 3%. So when you mix it, it's supposed to be somewhere in between, right? Okay, it should be somewhere in between. In other words, you do not expect that with 2% male and 3%, 2% of male left-handed, 3% of female left-handed. You do not expect that when you mix it, suddenly you have 5% of the population left-handed. No, that's mathematically won't be correct. Somebody's lying there. Either that person is lying about the proportion, or that person don't know how to do his math and therefore cannot share that person's opinion as a fact. That's opinion. That's not fact. And clearly from what our computation here, that's a wrong opinion. Okay? Yeah, it's not a fact. Okay. The fact is if you have proportion of two disjoint group, 2% and 3%, then the mixture should be between 2 and 3. You can go this way. I use this illustration. I know some of you high school, but once you sign up for West LA College, I have to assume you're mature. Okay, let's talk about the beer, Heineken. The alcohol level is, anybody knows? That's how you tell me that you drink Heineken. Alcohol level is 7%. Okay, and then another one, let's say Budweiser. I actually like to say Corona, but it could be sensitive for some people. By the way, I like Corona though. as long as I put some lime on it. You know. Now I'm not advocating for drinking. I'm a social drinker, so if we go to party, then I drink a little bit. I just hold the bottle, but I hardly drink it, so that nobody push me. Hey, you need to drink more. Hey, you need to drink more. I'm drinking it right now. I'm holding the bottle, just to make people happy. Okay. Now the thing is, like, if you have a can of 7% alcohol Heineken, and then a can of 7% alcohol Budweiser, and you put them together, what is the percentage of alcohol? Does the alcohol becomes 14%? No, you don't add the percentage. The volume is double. The volume is double. Okay, so let's say you have 1 gallon, if you are crazy enough to drink that much beer, right? So, okay, so 1 gallon of Heineken, and then let's say 2 gallon of Budweiser. If you mix them, okay, then you end up with how many gallons? 3 gallons. How about the alcohol concentration? Still 7%. Okay, let's do some computation. If 1 gallon of Heineken 7% alcohol means 0.07 gallon is alcohol, right? And the one here is 0.14 gallon alcohol. When I put them together, I still have 0.21 gallon alcohol, okay, over 3 gallons. That's still 7%. That's still 7%. Okay? So for the mixture, you add the volume, but the concentration should be in between whatever you have. You don't add the concentration. Well, by the way, this is actually Algebra 1. I teach this in my Algebra 1. Strangely, when I use, I feel it's really strange. When we use, for example, when I use a saline solution, like salt water, the saline solution, nobody pay attention until I change that to Budweiser and Heineken and Corona. Suddenly people pay attention. Now I have to do something quite exaggerated to grab students' attention at that level, you know. When it comes to mixture problem. Yeah, I have people who actually never pay attention. All of a sudden, they're doing some math. And strangely, that person who hardly do well in math suddenly do well when I change that into beer, vodka, even to the point of marijuana. Then that person get it right all the time. Seriously, that's the case. And I report that to my math chair. Such that I propose one day I need to have, we may have a textbook called Beginning Algebra for crack users. I was proposing this. Hey, you know what? I teach math regardless what's your background. I teach math to you regardless what you use that for. It is not my job to judge my students based on how they will use their math. Okay, my job is to teach you math. How you use that, that's your issue. I'm not a moral teacher, even though I'm supposed to teach moral. Okay, but some people call morality for something actually immoral from other cultures. So no, that is not my job. Okay, I will suggest you to use math for something goodness. Okay, but I have to admit that in the end, I will be proud if you use math however you use it. Okay, my job is teach you math. So if you don't know how your math, people will come to me. Okay, if you are not using math for a good thing, they will not blame the math teacher. They will blame your parents, maybe. They will blame you. They will blame your pastors, your imam, okay, your neighborhood, whatever. Okay, but when it comes to math, it's your math teacher. So let me get the credit for you if you use math for humanity or against humanity, okay? Because that's not my job to teach you those things. My job is to teach you how to use math. Well, anyway, coming back here, number 4. Okay, then the question is, what is the probability given knowing that person is a left hand? What is the probability that person is actually a male? Then, according to what we learned before, this is probability of the intersection male and left hand over probability of left hand. Okay, male and left hand is 0.09, I'm sorry, 0.0090 over 0.0255. Okay, so 0.0090 divided by 0.0255, that's 0.35. Okay, so that's the answer for the big question we have. What is the probability knowing that person is a left hand? This is the given. What is the probability knowing that person is left hand, that that person is a male? Okay, now let's do one more example. Let's do one more example. The example of what is good? The example of I have something in mind earlier, but I was thinking I may not want to use it. Is it okay if I use the example from coffee? Yeah. I want to use example from coffee because even though it's hurtful for some of you who already have, either you had that before or you have a relative already had that. But at the same time, I want to use this example because we all know more about this right now, and suddenly this becomes relevant. Okay, I can use another example, but if you don't feel relevant, you don't know how things actually work behind it, then we may have an issue. Okay, so I hope I get permission from you to use example from this COVID. Okay, this coronavirus. So here's the thing. Let's say 4% of our population, of a population, contracted COVID. Again, this number is hypothetical. Okay, now a new rapid, cheaper test is being put on trial. So they try to use this rapid test, and it gives 2% false positive and let's say 3%, no, make it 1 or 0.5. Okay, 0.5% false negative. Now, the terminology false positive and false negative is widely used in this kind of research. Okay, now then the thing is like, if a person is tested positive, using this test, what is the probability that person actually contracted COVID-19? Okay, so first I will do is construct the probability tree. Okay, so COVID-19, you actually having it is 4%, so not having it is 96%. Then from there, knowing that that person have COVID-19, 2% gives false positive. Oh, I'm sorry, false positive is when you don't get it, but you are tested positive. This is for false positive. This is false positive. This is false positive. It shows positive, but actually it's not right. Okay, and is 0.5 false negative. 0.5% false negative. Now, false negative means the test shows negative, but it's supposed to be positive. Okay, that's the information. Now, then from there, we go on. Okay, so if 0.5% shows negative there, then this will be 99.5%. If 2% show positive, then 98% show negative. Okay. Part B. Then what is the probability somebody contracted COVID-19? I'm sorry. What is the probability somebody actually tested positive? If you take the test, not knowing you are positive or negative, not knowing you are actually having COVID-19 or not, what is the probability you are tested positive? So you may be tested positive while it is actually wrong. Okay, just like you may be tested negative while it's actually wrong. Okay, so to be tested positive, either you actually have that and tested positive, plus you don't have it but tested positive. Now this will be 4% times 95% plus 96% times 2%, right? So tested positive is this track here and this track here. They are mutually exclusive. That's why we add them. Then this will be fast forward, 190.38. So this is 0.0380 plus 0.003 192. That is 0.0572. So 5.72% of those people who take the test will be tested positive. Notice that this 5.72% is between 2% and 99.5%. Oh, I'm sorry. This should be 99.5. This should be 99.5. So I miscomputed there. This is 99.5%. So I miscomputed here. Good thing I checked. So let's see. 398. 0.0398. So 5. This is 5.9%. So this 5.9% is actually between the 2% false positive and 99.5% correct positive. Okay. So our number will not be wrong. And the third one, so in part B there, I actually do step 2 and step 3 at the same time. And what is the probability that person actually have COVID-19, knowing that person tested positive? So this is the probability of tested positive below and probability of the intersection above. 0.0590 here and 0.0398 here. And 0.67458. That's 67.458%. So if I am tested positive, what the probability that I actually have it is approximately 2/3, approximately 67%. Okay, well, because this new rapid test, new cheaper rapid test being proposed to be used to replace the test that we had originally. Okay, we just want to have that faster, cheaper, okay, and not relying on the older method. Yeah, so you have heard something called rapid test in Indonesia. That's we have that something called rapid test. So you get the result within 10 minutes. There's swab test that takes like around two days. I'm not sure about the one we have here in America. I'm not really updated recently. Okay, so suppose somebody invent a newer way, a new cheaper way, then how accurate will that be? Oh, by the way, the accuracy of this test is equal to the probability that somebody have the COVID and tested not positive, plus probability somebody don't have it and tested negative. That's the accuracy. Okay, that's the accuracy. There's a word called sensitivity. That's the sensitivity refers to that you actually have it. Hold on. I think I want to say that sensitivity is this one. is probability that it's tested positive, knowing that that person have COVID-19. Let me put a question mark here. That's the terminology that I forgot. There's something called sensitivity, and then there's another one. I forgot. But let me give myself a break first. Right now it's 9:10. Let's say we come back at 9:20. And I want to check that